this or that. So we just don't know. Okay, and I've thought about it a lot, and I was actually going to talk about some of these mechanisms, but I will probably run out of time.
But we could still have like splits using higher scale supersymmetries. It's like not ruled out. It's just like it doesn't explain.
It's not ruled out.
Yes, it's like we could just have higher energy symmetries.
Yeah, and there's some thinking about how split could it be and why would that be and so on. And I've done a lot of that, but I can't get it out in the short time I have. In fact, the even shorter time I have.
Thank you.
Sure.
So I think I'll need that.
Oh yeah, sorry.
I made a good joke yesterday.
Gotcha.
If you're the Jedi, what am I? The Darth Vader.
Yeah, I think so. In fact, you were once one of the Jedi. And
Oh,
you're
yeah,
abandoned it. You turned your back on it.
Yeah. Maybe just a Sith Lord, because I don't do dark matter much. You really went to the dark side.
So now David Shih is going to do dynamic resistance breaking.
Well, I think that's everything, right?
Yeah. Okay, good. So we've had 2 lectures so far, and in those 2 lectures, I've gotten to the point, I think, where I've explained what a neural network is, how we fit them to data, and all that. So we're ready to look at some applications. And originally, I had planned for 3 applications. And that was supposed to start last lecture, and then this lecture would be a different one, and then the last lecture would be a third one. But I think we're going to probably run out of time. So I have to decide to cut something. And I'll still talk about all 3 applications, but I might not go into as much detail. Okay, but anyway, we'll see how it goes. So I started to lay out the first application, which is to top tagging last time. And so the problem is, how do we distinguish top quarks, which decay to B and W, which then subsequently decay to 2 more quarks? How do we distinguish these from just light QCD jets that shower according to QCD? Okay, these also shower according to QCD, and so as I said last time, what we get out are, at least for tops, we get out these fat jets, which are bigger than usual jets, and have a distinctive, on average at least, they have a distinctive 3-prong substructure. Okay, where 2 of the prongs make a W. Okay, whereas QCD jets tend not to have that substructure. Okay. And so we got last time as far as discussing some of the physics features that could be used to distinguish between these two. Okay, so some useful physics variables include mjet, mw candidate, and this thing called n subjettiness. Okay, so that's three very powerful features. Okay, so in the language of machine learning, we would call these high-level features that are engineered by people, right? So they're human engineered. Okay, and then what we're going to explore at the beginning, the first part of today's lecture, and I have a demo prepared, is we're going to explore alternatives to that. So what's the promise of modern deep learning? Is there a question? Yeah.
Yeah, I was just wondering, in terms of useful physics variables,
Mm-hmm.
would jet width also be useful, or is there some reason it's not included?
Yes, so the list does not stop there. You can keep going. Yeah, I'm just trying to keep things sort of simple. Yeah, so there's other measures of the jet substructure, things like width might be good, yeah, that people have come up with. And yeah, you can throw all these features at it, and qualitatively, what I'm going to tell you is not going to change too much. Yeah, okay, good. So yeah, so in some sense, this is like a straw man because I'm only using 3 features here. And so you could argue that if you use 10, you might get a better result or something. But I think the general story is going to remain true. OK, so yeah, so what do we want to try out that's an alternative to this, right? So the promise of deep learning is that we can extract features like this out of low-level information. OK, so train neural networks directly on low-level features or low-level inputs. Okay, so what's the lowest level input that we would imagine doing? Well, okay, not the lowest level input. The lowest level input would be what is literally read out by the detector, which are like hits and things like that, right? So what's one step up from that? That would be a nice playground for our techniques. That would be like looking at all the constituents inside the jet. So this jet is actually, right. So this is just schematic, and this is just a representation of sort of the 3 partons, right? But partons don't stay partons, right? They shower, and then they hadronize, right? You learned about that, I think, in previous lectures, right? So in fact, in a real jet, there's all these particles inside the jet. Okay, each particle tends to be a hadron. So there could be something like 100 hadrons inside each of these jets. Okay, that maybe the bulk of their energy is centered here, but there's a lot of stuff still going on, and a lot of information there. Okay, so the promise of deep learning is that we can train neural networks directly on, say, let's say, for example, the momenta, the 4 vectors of all the hadrons in the jet. Okay, so you can think of those high-level features as specific functions of these 4 vectors, right? How do we get the jet mass? We add together all the 4 vectors inside the jet, and then we compute the invariant mass of that, right? So these are all just specific functions of these 4 vectors, okay? And the idea is that the neural network can learn these functions if they're useful, and it can learn any other functions too, okay? So we're going to train neural networks directly on the 4 vectors of all the hadrons in the jets, and we're going to compare the classification performance to if you use the high-level features, And so this is called automated feature engineering. Yeah.
To be clear,
Mhm.
that I understand what you're saying.
Yeah.
When the LHC gets out data, it's like pixel readings and
That's
stuff
right.
like that, right?
Yeah,
So
yeah.
you're saying we pre-process that into 4 vectors and then we feed that in here?
That's what I'm describing here is, let's say, so where some medium level of information or representation of the data. Yeah, the real representation of data is like hits in the tracker, blobs of energy in the calorimeter. Then they have a step where they reconstruct particles, right? They say, oh, this particle was an electron, this particle was a pion, something like that, right? So that's the level we're going to operate here. You could imagine some future neural network does even better than that with the even lower level data, but we're not going to talk about that here. Yeah. Good. Any other questions? Yeah.
Since these variables have like various constellations, can you just throw them in as input like with the other low-level inputs?
So you mean put these in as an additional? Yeah, you could.
As well.
Yeah, yeah. In fact, I'll show you an example where that is essentially done.
Okay.
Yeah, I think. Good. Okay, good. So let me introduce the data set. Okay, so I'm going to do a demo on the laptop, which you can also do at home. And this demo is based on it's called the Community Top Tagging Data Set. And this is the reference if you want to see. It's still reasonably state of the art because, so yeah, there was like a challenge, okay, like a public challenge. ML people love these challenges, right? So the people in our community, they decided, let's do our own challenge. And so they did a top tagging challenge. And I think it was very successful. So it got many of order 20 or 10 or 20 contributions. Everyone tried out different techniques, different data representations, different architectures, and there was a clear winner. So one of the approaches really did much better than the others. So that was like a breakthrough of sorts. And yeah, so this is still reasonably state of the art. So I highly recommend you check it out. And part of the value of this challenge, besides innovating new ways of doing top tagging, is also this data set is public and lives on. So people still continue to play around with it. Okay, so what is this data set? Everything was simulated with Pythia and Delphis, okay? And there are 1 million top jets and 1 million QCD jets. Okay, I'll spare you the details of how exactly they were defined, but suffice to say that for each, the 200 highest PT constituents were saved. Okay, so out of every jet, they saved 200 highest PT constituents, and in many of the jets, there weren't 200 highest PT. There weren't 200 constituents, so then they just zero padded to get to 200. Okay, and this was each one was split up into 600K train, 200K val, and 200K test. Okay, so you weren't, usually when you train with more data, you get better performance. So to keep things fair, you were supposed to only train on the first 600,000 jets of each type. Okay, good. So, yeah, so in this challenge, people, I mentioned the data representation. So people considered many different representations of these jets. So you start from the 4 vectors of the constituents. So that might be PT1, eta1, phi1, PT2, eta2, phi2, ... Okay, so that in and of itself is a representation of the data, a low-level representation, right? And of course, then you have the question, So the neural network, the fully connected neural network I described last time is not permutation invariant. It cares about the order you feed in the data. So should I feed in the 4 vectors ordered by PT, by something else? It wasn't totally clear, so people tried different things. Okay, but that's an example of a representation, is these 4 vectors plus some ordering of them. So I guess, yeah, this goes under the topic of data representations, which is an important part of the story. Okay, so another way we can represent the data, which is very intuitive, I think, is these things show up, the jets show up in the calorimeter, right? The calorimeter is automatically pixelated. It has cells, right? So it has sort of a finite resolution already. And so why not represent the data as an image? Okay, so that was an idea that preceded, in our field, that was an idea that jet images was an idea that preceded this top tagging challenge, but people, including myself, tried it out. Okay, so you might have a jet with a lot of energy here, and some energy here, and some energy here. So that would be another representation of the data, jet image. Okay, yet other people thought, well, maybe I can think of this not as one big column vector, but as a sequence. What if I think of it as a sequence? It's not terribly well motivated by anything, but you know, what if I think of it as a sequence? Oh yeah, so sorry, if you work with jet images, then the ML people have invented an architecture that's very well suited to image recognition. And that's something called the convolutional neural network. So if I had more time, I could go into more detail about what that is. But suffice to say that that is something like the DNN I talked about last time, but that works on images. Okay. And similarly, if you think of the data here, each jet as a sequence, okay, then so what is the premier sequence, like time sequence that we encounter in the real world? Language, yes. So good. So natural language processing is a huge branch of ML, right? And works with sentences, words, sentences, paragraphs, books. So those are all sequences. Yes?
I'm not quite understanding the difference between 4-vector and sequencing. Is that kind of the same thing?
It is, yeah. So if I think of it just as a big column vector, it's very natural to feed that to the DNN that I talked about last time. If I think of it as a time series, then it's natural to feed it to something else, which I'm about to say. Yeah, but it's the same information. Yeah.
I mean, it seems like it's the exact same information, right?
That's right. Yeah. In this case, you lose some information maybe from the pixelization. In this case, it is the exact same information. Yeah. It's just that there are architectures that have been constructed to handle sequences.
I see.
Yeah. That are maybe if the sequence has some like long time correlations or something, then those architectures, if the sequence has some semantics, then, or not semantics, sorry, syntax, then they could learn it from this representation. Yeah. I'm not sure that the 4 vectors inside of a jet have syntax or long time correlations, like correlation between the highest PT and the 100 highest PT 4 vector. I don't know. But yeah. Was there another question?
That was my question.
Okay, good. Yeah.
So I think you mentioned previously there's no timers on the detectors, so right? So you don't know the time.
This is not real time. Yeah, this is like a ordering of the jets by, say, PT, and let that be our time. Yeah, exactly. Yeah.
So you can, in principle, just shuffle the sequence and fit it into it. Like there's no like
Canonical. Yeah. I agree.
Why does the time series
Is a good idea?
Yeah.
I'm not sure it was a good idea. But people tried it. Yeah. You'll see the proof. You'll see the results. Like I'm gonna share with you the plot from this paper. You'll see how the different approaches did. But okay, so there's different architectures that people came up with to handle sequences like RNNs, something called a LSTM, lots of alphabet soup. I'm not sure. There's a new thing out on the market called transformers that are state of the art now. I don't know if anyone in our field used them in 2019. I don't even know if they existed yet in 2019. But anyway, OK, so this is just some examples of the different representations of the data. OK, good. So one last thing I want to tell you before we go to the demo is, OK, so in the demo, we're going to train some neural networks and get some classifiers out. So how are we going to, what does it mean to have a good classifier or a bad classifier? So how do we measure the performance of the classifier? So we need metrics, yeah? OK, so in general, what do we want our classifier to do? We want it to select as best it can the top quarks and reject as best it can the QCD jets, right? So there's different ways to quantify how well that does, okay? So one metric is the loss itself, right? The loss is the thing that we train it on. The one that achieves the lowest loss should be the best one, okay? The problem with the loss, the reason we don't typically use the loss as a metric is that it's not very intuitive, as you'll see compared to the other metrics that I'm going to write down. OK, so good. So the other metrics I'm going to write down, I guess, are more expressive or intuitive. And they all start from the way that we actually use this classifier. So the classifier gives us a function, right? And it's a function that takes a jet and gives us a score, right? And a high score would be signal-like, and a low score would be background-like. Okay, so what am I drawing here? These are histograms of all the jets. Yeah. So I take all my signal jets, my top jets, make a histogram of their scores, and a good classifier will peak over here. And then I take all the background jets and make a histogram of their scores, and a good classifier should peak over here, right? OK, and so what we actually use this classifier for, usually, is we imagine putting a cut on it. Say, give me all the jets that satisfy some f above some threshold. OK, and eventually we'll say these are our top jets. R, yeah? OK, so there's what we're going to say at the end of the day are our top jets. OK, of course, as you can see from this histogram, there's going to be some mistake I make, right? And also, as you see from this histogram, there's going to be some signal that I throw out, right? So those are the two important metrics, I guess, is for every cut on the classifier score, we're going to get a pair of numbers, the signal efficiency and the background misidentification rate, the background efficiency. Okay, so this is this is how much I throw out. So above this is the signal efficiency, and then this is the background efficiency. Okay, so every classifier you can think of is described by, so this is a function of the threshold, right? So as I vary the threshold, I'm going to move around in the space, right? So that finally gets me to the metric that everyone uses to tell you how well your classifier is doing, and it lives in this space. So the ML people like to draw it like this. Okay, so if I do nothing, so I don't cut at all, epsilon s and epsilon b are 1. They're both 1. And if I cut up here, then they're both 0, right? And as I slide this cut from here to here, I'm going to sweep out a curve, okay, in this space. And so this is called, I don't know why, but this is called the rock curve. This stands for receiver operator characteristic. It's something to do in signal processing or early days of radio, or I don't know, radar people in World War II. I'm not sure. So anyway, it's called the ROC curve. And that's what everyone uses, we all use to quantify how well we're doing. And so this is better, yeah? So in this plot with epsilon s versus epsilon b, this is better. Okay, the perfect ROC curve, which you can never achieve, would look like that, right? Okay, and good. So the ROC curve is a curve, and we can plot this ROC curve, and we can compare different classifiers, see which one has the better ROC curve. It's also useful sometimes to put a number on it. Okay, so 2 aggregate metrics you can use that tell you how good your ROC curve is. One of them is to measure the area under this ROC curve. Okay, so the area under this ROC curve is called the AUC, area under the curve. Okay, so AUC equals 1 is perfect, and AUC equals 0.5 is random. Yeah, we should also keep in mind what a random classifier would do. If you had the worst possible classifier, so somebody hands you a jet and you just flip a coin, okay? You're fired, but that's that curve, okay? So you can, as a homework exercise, you can convince yourself that the random classifier gives you the diagonal line, which has an AUC of 0.5. Okay. So yeah, so that's a very popular metric, commonly used metric. And another single number you can put on this is called the accuracy. Okay, so given some threshold, how many signal jets do I classify correctly as signal jets? How many background jets do I classify correctly as background jets? And then what's the maximum of that? So I could define that as the maximum of epsilon s plus 1 minus epsilon b divided by 2. Again, 100% accuracy would be perfect, and 50% accuracy would be random. Okay. Yes? Yeah, so imagine varying my threshold, and then, so maximum over the thresholds. Yeah. 1 minus epsilon b. That gives you how many fraction of backgrounds you correctly tagged as backgrounds. Yeah. Okay. And the last metric I want to talk about is in high energy physics. So yeah, so this way of presenting the ROC curve is conventional in ML because they typically are dealing with balanced classes, like equal number of signal and background. We in high energy physics or at LHC usually are dealing with highly imbalanced classes. So there's way more QCD jets than top jets. And because of that, we like to plot things differently. So slightly different way of visualizing the same information is this thing, 1 over epsilon b, is called the background rejection factor. Okay, and so we like to work in terms of that, and then in that space, usually typically a ROC curve will look something like this. If you take that curve and transform it into this space with so we like to also plot this on a log scale, okay? Something like that, and then it'll look like this. Okay. And in the top tagging challenge, I guess the experimentalists tell us that a useful working point for a top tagger is to have 30% signal efficiency. Okay, so then the value of 1 over epsilon b at epsilon s equals 30%. This was a metric that was used in the top tagging challenge, which we called R30. Okay, yes, so that's all the background information you need to know. Yeah.
Is the ratio of signal jets to background jets something that the network can learn itself?
Yeah, so first of all, in the supervised task, we train them in balanced classes. Yeah, that's always going to give you the best classifier. When you apply them to data, the real data is imbalanced. So that's why we want to strive for a very high background rejection factor. Now, your question was in the data or in the training?
I guess maybe a better question is thinking about like LHC data, which is imbalanced. Why would you train it on a balanced data set and then you know, test it train it and test it on a balanced data set and then use that network for your unbalanced data set?
That's what we're doing.
Okay.
Yeah. That's what we're doing. Because if you train with very imbalanced classes, you get usually a worse result. There's a lot more noise associated with the smaller of the two categories. So that's what we're doing. Yeah. Yeah, sorry. I just meant to indicate that it's on a log scale, so that's 10, 100, 1,000. Yeah. Okay, so let's look at the demo. I think that's everything I wanted to say. Yeah. Okay. So now, do I do all this technology stuff? Okay. We've got to bring the screen down. Did anyone try to run it last night? Nobody? Yes. You get the A. Okay. Well, okay, so good. So I'm going to go through it. Maybe that's why you didn't bother to run it. Okay, so this is a Jupyter notebook, a Google Colab notebook, which anybody can run. And so what I've done here, so this is called part 2. You can also find on the Google Drive part 1, which is how I calculate these high-level features. So if you really want to see like how everything's calculated, you can. Part 2 takes the result of that calculation and loads it. Okay, so I have these data files that contain these 3 features, MJet, MW candidate, and tau32 for all the QCD and top jets. Okay, so we load them. Oh, they also have the labels inside of them. 1 for tops and 0 for QCD. So here's a plot. Can you see that? Yeah, good. Okay, so here's a plot of the 3 features, the high-level features, showing you good, separation between signal and background. Okay, and the first thing you would try is not machine learning, right? The first thing you should try is what can I get with just simple cuts? Okay, so no machine learning, just cuts. And so that's this attempt to do cuts on all 3 variables. So here I'm saying I want to cut in some window around the top mass, some window around the W mass, and I want to cut on end subjettiness. And I'm going to count how many pass the cut and how many fail the cut, and that's going to be my signal efficiency and my background efficiency. Okay, so I plot all the signal and background efficiencies I get from all choices of cuts that I scan over, and I don't get just one ROC curve. I get, in some sense, a family of ROC curves. So that's what's shown here is all the different working points. So each one of these dots corresponds to one choice of the cuts here. Okay, so you see that there's definitely an envelope that's being swept out, which is like the best you could do for a given signal efficiency. What's the best background rejection you could do? There's some best cut that you could do. Okay. All right, so that's the baseline, okay? And then here you can see what happens if you train a neural network. This is an intermediate point, but what happens if you train a neural network on the high-level features themselves? Why not? So in some sense, that's going to find the best set of cuts in an automated way. Okay, and so here's where, I don't know if this were a different set of lectures, I would be telling you about how Keras works or something, but these are the things which, these are the commands or whatever that you'd want to know to build one of these neural networks. Or the general framework for that is something called Keras, if you haven't heard of it before. And that's built on something called a backend, which is called TensorFlow. Okay, so this is a product that Google puts out, but it's open, I think it's open source and anybody can use it for free. Okay, so good. So here I define a very simple neural network. And maybe the only thing you would want to take away from this going by so quickly is maybe just how few lines of code it takes to define one of these things. Okay, so they like Google, have made it very easy for us to do this sort of stuff. Yeah. Question?
Do you prefer Keras over TF-Learn or other things?
In the next demo, which I may cut from the lectures, but I'll put it on the Google Drive, I show you another example where we use Pytorch, which is another framework. Yeah, so basically Google put out a framework. Actually, first, I think the University of Toronto put out a framework called Theano, but then Google put out Keras, and then Facebook put out something called Pytorch. Those are so now Keras and Pytorch, I think, are the most commonly used frameworks. They do basically the same thing. Okay, so anyway, so maybe takeaway message here is just how simple it is. It's not very complicated to define one of these things. So based on what we've learned in the first 2 lectures, you can see this is a fully connected neural network with 2 layers. Okay, so there's an input layer, which is not shown, and then there's 2 hidden layers with 64 nodes each, and activation given by ReLU. And then it outputs to, I've chosen to do 2 output nodes to have it both signal and background probabilities, but that's sort of overkill. But anyway, that's what's happening here. Just think of it as it's outputting probability of signal and probability of background, but they have to sum to 1. So there's no additional information. This is commented out, but if you want, you can train it with additional regularization. Here I specify the batch size that we're going to train it with and how many epochs. Okay? Here we specify the loss. So this is just the binary cross entropy I mentioned, we talked about before. And this specifies how we optimize this neural network. And so here we use the ADAM algorithm with the default parameters. And that's pretty much it. So then we prepare our training, validation, and test data. And one little sort of annoying thing about neural networks is that they tend to, they're not scale invariant, so they tend to prefer inputs that are order 1. So in this last step, I've rescaled the inputs to be order 1. And if I didn't do that, which you should try at home if you want to learn about this stuff, you can see what happens if you don't rescale these to be order 1. Okay, and then finally, we fit the model. That happens here. And here you can see after every epoch, I'm not going to run this code because it would take too long, okay? But after every epoch, actually this tells you how long it takes. So every epoch in this case takes 30 seconds. And I guess it's not necessary maybe, but yeah, this is being run on a GPU. So that's the other thing. So Google Colab, in case you weren't aware, gives you access to GPUs. They kind of throttle it a bit, but for simple things like this, it's very usable. So even if you don't have a GPU at home or in your institution, you could do a lot of things for free with Google Colab. Okay, cool. So yeah, here we do the training. After every epoch, it prints out some metrics like the loss and the accuracy. And here we can monitor for overfitting. So we see, I'm not going to do it in detail, but you could just see by eye that the validation loss and the training loss are not diverging too much. So that's good. And then after all is said and done, we can visualize how the accuracy of the classifier increases with the training and how the loss decreases with the training. And then we can calculate the scores, some of the scores I was talking about before. And finally, we can make a ROC curve. So this is the ROC curve that you get from training a simple DNN on the high-level features. You can see that it matches what we did with cuts as to be expected. Yeah?
On the test validation plot that you just showed a couple of
Mm-hmm.
what was that one?
Yeah, this is train and validation. Yeah.
You had a slightly different right here. So this looks like the example you showed for a sign of overfitting. I guess it's a very small number, but this kind of dip in the val and going back up.
Okay, yeah, so there's some like noise here. That's true, yeah. This could be because the validation set is a factor of 3 smaller than the train set.
I guess we'll also zoomed in.
Yeah, this is 0.906, 0.907. So yeah, so these wiggles do happen and could be a sign of just finite statistics, yeah. Good. Okay, so that's the ROC curve you get, and this is the R30 metric I mentioned before. It's 400 for this DNN. Okay, next we can, are there any questions about that? Yeah.
How do I interpret that? Like, is that
Well, there's two ways you can answer that question. In an absolute sense, so that depends on what application you want to do with this, right? So maybe there's some top, so yeah, that's also another way people talk about these classifiers like purity. Purity is another metric, right? So, so it depends on your application. Like maybe you're doing a standard model measurement and you want a very pure sample of tops. Or I don't know, maybe you're doing a new physics search for Z prime to TT bar, decaying to TT bar. And then maybe you don't care as much about backgrounds because you're going to do bump hunt or something. So it depends on your application. The other way to answer that question is relative. And that's how we're going to approach it here, because we're not going to put this all the way through some application. So we're going to see that this ROC curve gradually gets better and better the more things we try. And so that's like a factor of improvement is just generally a good thing. Does that answer your question? Yeah. Good. Yeah.
So when you're using a neural network to do some classification problem or whatever, and you want to associate error bars to your measurement essentially. So you can only use the test data error rate as the for your error bars, right? But you don't know if your actual when you use it on the data, you're getting the same error rate.
Good. Yeah. So okay. So first of all, uncertainty quantification with neural networks or machine learning is a big subject, and I don't have time to cover that, unfortunately. But you've touched upon a general problem with supervised learning, like in our field, where we use simulations, right? What if the simulations aren't good enough, right, or they're not accurate? So then, has this thing learned something about simulation that is not reflected in real data, right? So I can put a reference, maybe if I remember to, or you can remind me to, where. Like, so CMS and Atlas, they will take these methods and they will commission them on the data, and they have a whole procedure for training them on simulation and then measuring their performance in data using control regions and signal regions. And then they'll derive basically scale factors between the performance they thought they were going to get and the performance they actually got. And then they'll calculate uncertainties on those scale factors by like varying things, as they do. So that's the extent to which I think in general that CMS and Atlas try to deal with this problem.
Is the control region like comparing with another method, like the high-level features?
No, I meant control region. Literally, like they'll define a background-rich or top-poor region and try the method out there. Yeah, and then a signal-rich region, they'll try the method out there. Yeah. So usually they'll use something like the top mass window to define or they'll do like a anti-B tag or something to define, or in a TT bar event, they'll say if one side goes semi-leptonically, then the other side is probably a top, something like that. Yeah, but yeah, so the mismatch between simulation and data is a concern here, and you have to deal with it. Yeah. But what they find typically is that the simulations are pretty good and the scale factors are at like the 10% level. So, and that's good enough for many applications at least. I don't know about standard model precision measurements, but it's good enough for BSM searches. Yeah. Okay, so good. So the next thing I do here is to train a DNN on the jet constituents as promised, okay? And so I do some pre-processing of that. And we only take the first 30 constituents, in part because Colab runs out of memory. But yeah, so we pre-process and read in the data, and we define a bigger neural network in this case. But again, I didn't optimize any of these hyperparameters, but this neural network has 4 hidden layers with 128 nodes each. Otherwise, it's the same idea. Oh, I should have mentioned, this tells you how many parameters the neural network has. So this neural network has 60,000 parameters, which is a relatively small neural network. And then we train it here for 15 epochs. And we can see the performance. Yeah.
Is the input the 4 vectors?
Right. So the input are all the 4 vectors. So here you see, this is the input. It's all for the validation set. It's 30 of the highest PT constituents, and the three vectors, because all the constituents are massless. So the PT eta phi for all the constituents. Yeah. Yeah, they're sorted by, so they're the 30 highest PT and then sorted by PT. Yeah, that's a choice though, yeah. Okay, so good. So then we have all the same plots and let me cut to the ROC curve. So here you see the performance of feeding all the constituents or the 30 highest constituents to a DNN. And it's actually not great, right? Or you could spin this two ways. You could say, well, I recovered more or less, oh, sorry, the yellow curve here is the performance of the DNN, right? So you could say I recovered the performance of the high-level features without putting in any physics knowledge. I didn't do better than the high-level features in this case, but I did match the performance. So who needs smart physicists, right? Okay, yeah.
Are the high-level features like truth level from the simulation?
Yeah. Mm-hmm. They were computed from the same constituents. Yeah, they're using the same information.
To do better than the high-level features?
Ah, good. Okay, because there's more than just those 3 high-level features. Yeah, like I think you asked earlier, there might be more high-level features you could include, but maybe there's like an infinite number or something. Maybe there's a lot, right? Yeah, so the high-level features are just one compression of the, say, 30 highest PT or 200 highest PT constituents down to 3 numbers, right? But there's really a lot more information in those constituents. Yeah. Okay. But here we recovered the performance. Actually, R30 was a little bit worse, but overall the ROC curve is more or less consistent. Okay. Now, I added this bonus, but I didn't have time to tell you what a CNN is. But anyway, I thought it would be fun to visualize the jet images. So I prepared some data too, which are jet images. And here's the code that you can run to visualize them. Oh, the jet images are too big to fit into even our server's memory. So, so I had to do some tricks here, which you may find useful using something called a generator to only read in little bits of them, sort of batches of them, instead of reading them all into memory. Anyway, so good. So these jet images are 37 by 37. And if you they've been preprocessed, so rotated and flipped. They've been preprocessed, so they all sort of point in the same direction. And so if you take the average, you get a nice result. So this is the QCD average jet image. And this is the top average jet images, showing you the 3 lobes here. Yeah? Yeah.
I guess I'm surprised that when you average all the tops together, that you get the subjects all in the same place. I know we rotated them so that like
Yeah.
they had this, but like, I would still expect that the subjects might move around a little bit.
Yeah, so the distance between the subjects is fixed by kinematics, like the W mass and the top mass. So that is fixed because these are all generated at the same PT. I didn't tell you that, but they're all generated with the same PT. So the distance between the subjects is more or less fixed on average. So by doing the rotations, we take care of the remaining degree of freedom, and so we get a nice average. Yeah.
When you say rotations, you're saying aligning blobs?
Oh, right. So okay. So collider physics. I don't know if you. So you learned about eta and phi, maybe. Okay. So this is in eta and phi, but the jets have a sort of a symmetry in eta and phi, at least locally. So I can rotate in eta and phi, and at least locally, and not affect the physics. So that's what we did to make these images, or make these jet images, is to rotate them in eta and phi space. So this is like a rotated eta and phi coordinates now. Okay, so we feed these to a CNN, and this is how you define a CNN in Keras. Again, it's a little bit more complicated, but you can look all this stuff up. It's very standard stuff. And then now the CNN has 600,000 parameters. Okay, so a factor of 10 more parameters than before. And correspondingly, it's a lot slower to train. So now each epoch takes 10 minutes to train. So I did 10 epochs here, so this took about an hour. Okay, and then we crunch out the results, and we see some improvement. Yeah, so this is the ROC curve of the CNN, and the R30 went up to 673. So we outperformed the 3 high-level features, but it took some effort, right? Okay, and then any questions about that? Yeah. Good. So that I pasted the state of the art from the reference into this notebook, so I wouldn't have to open a different PDF. So these are the results of all the challenges. The CNN is the one I just presented that my student Sebastian and I did. And here's the best one, ParticleNet. So it got a R30 of 1300. So pretty big improvement. Yeah, we started from 400, so that's like a factor of 3 background rejection. So I think that's significant, and it's like getting free data, right? We get to reject 3 times more QCD background while keeping the same number of tops, right? Or if we had wanted to, yeah, anyway, it's like with the same amount of data, we're getting much more out of it. And then what is GOAT? So GOAT, so we had the idea at the end of the challenge to take the predictions of all these different methods and train a neural network on those. So a form of ensembling. So thinking maybe each one learned something different, slightly different. It was interesting that actually that did improve the performance. So the GOAT is ensembling all these together and raised the R30 a little bit more. Oh yeah, and that is getting back to the question: could we have added the high-level features to the DNN or the CNN and gotten better performance? And one of these here is using high-level features, I think. Yeah, like this one here, multi-body and subjectiveness 6 is using high-level features. So when we did the GOAT, that was like that. Yeah.
I think I don't quite understand what's going on with the GOAT because the number of parameters goes down compared to the
No, yeah, that's a misleading. So that's just the number of additional parameters for the small DNN that we trained on all the outputs of these guys. Yeah.
How are you doing the ensemble exactly?
We're literally just taking the classifier scores from each of these approaches and treating them as high-level features. And then we're feeding those to another neural network. Yeah, yeah. Yeah.
Can you degrade the performance by adding more and more variables?
Degrade the performance?
Yeah. Or are you guaranteed to have at least the same amount of performance?
Well, yeah, that's a good question. So, like if you just add random noise to the problem?
Something I built from these low-level features.
No, I mean, yeah, usually that doesn't happen. If you were to just add noise to the problem, like a dummy feature that has no information, you could potentially confuse one of these neural networks, potentially. But with supervised and balanced classification, in my experience, usually you don't spoil the performance. It's smart enough to like just ignore that noise.
So when in doubt, just put all the features you can pick up.
I think that's this is saying, like, if you want to get the absolute best classifier and not understand any physics, yes, just do that. Throw the kitchen sink at it. Yeah. Which is, if you don't, for many applications, having a black box is fine. Like if you just want to tag tops and look for new physics, that way, this is just a tool, just like b-tagging or something. So in that case, that is probably the correct approach. Yeah. Mm-hmm. Yeah. Oh, good observation, yes. So you notice that the AUC is not a very informative metric, right? So let me show you the ROC curves here. So these are all it doesn't fit on one. Okay, so these are all the ROC curves of all the different approaches. I should say, by the way, ParticleNet, which was like clearly better than the other approaches, is an interesting data representation. I forgot to mention it, but there's another way of thinking of the data as what's called a point cloud. Point clouds, I guess, are of interest to people doing self-driving cars because the cars have LiDAR and ping the surroundings. So they don't like take a picture of their surroundings. They take a radar or LiDAR three-dimensional representation of their surroundings. So what they get back is a point cloud. So it's a collection of points which, at least at first, doesn't have any structure to it. And so ParticleNet starts from that idea, is let's think of all the constituents of a jet as essentially nodes in a graph with no a priori structure. And then there's a technology that ML people developed called graph neural networks that they took off the shelf, basically, and applied it to the top jets, and they found really good. That's the blue curve here. They found very good performance. But in answer to your question, the AUC is sensitive to the behavior of the ROC curve over here. And so whereas the R30 is sensitive to the ROC curve here. So the AUC, if you care about the performance over here, the AUC is not a very good metric. Yeah.
What did the worst performing
There were no losers here, just a winner. They did something unsupervised. They tried to do something unsupervised. Yeah, they said, let me throw together both tops and QCD into one bucket, no labels, and then try to do classification with no labels. So much harder problem, yeah. Yeah, so no losers, okay. All right, so that's everything I wanted to say about top tagging, I think. See how much time I left for myself. Oh gosh, okay. Yes? Okay. Yeah, so I want to now switch gears to a different topic, as promised from the outline. So I want to talk about something completely different, which is generative modeling. Okay, I think I can shut this off. Okay. I should say the top tagging is not dead. So the person who did ParticleNet has continued to work on it. And just this past year, they had a paper where they almost doubled the R30 again. And the innovation there, actually they had two papers where they doubled it in two different ways. One is using this transformer network, and the other is by doing the ParticleNet but with Lorentz invariance. So that was cool because it put some physics into it. Yeah, so basically by putting in a symmetry that has to be in there, they were able to get sort of more out of the data. Yeah?
By using the transformer, can we learn anything from that? Like the fact that using just language processing stuff on the data, is there something to learn from the fact that there's a pattern there?
Well, I think at least the way they wrote their paper and the way I understand it is the virtue of the transformer and the ParticleNet approach, and for that matter, the CNN, is that they're permutation invariant. So there is a symmetry here, big symmetry, which is that its top or not top does not depend on the order of these constituents. So the classification score should not depend on that, ideally. And so the CNN does that by pixelating everything. And the ParticleNet does that with the graphs. And the transformer is something called self-attention, is constructed to do that. I don't know why the natural language people thought that was a good idea, because the order of words in a sentence do matter. But anyway, that's what they do. Yeah. So that's the part of it that's actually useful. It's not like the language itself, I think. Yeah. Okay. Good. So now we're ready to start lecture 3. All right. So a new topic: generative modeling and density estimation. Okay, and I'm presenting it in this way because it's going to get sort of successively more, I guess, complex, or you might say interesting. But the building blocks of this are still what we've covered so far. So these things that I'm going to talk about are still built out of DNNs. They're still trained with SGD or Atom. So the building blocks are the same. Okay, but yeah, this is another, so we talked about classification. Now this is another thing you can do with neural networks that's very cool and has many applications to our field. And this is an unsupervised method. So we learn from data. The idea is, can we learn from data the underlying P of X and sample from it? Okay, so can we learn the probability density that the data was drawn from and then sample from it? So we might learn P of X maybe, possibly, implicitly. Okay. And so this has many applications to HEP, to our field, which include, so a big application in general, I think, is something which goes under the umbrella of surrogate modeling. The general application, which maybe you have one in mind, is if you have a very slow but accurate simulation, or some slow but accurate calculation that produces, let's say simulation, so it produces examples. and then you want to shortcut, you want to speed it up. Then what you can do is train one of these generative models on the results of that simulation, and then it can basically shortcut all the physics you put into the simulation and just generate more examples that look like it. So that's surrogate modeling, and the example I'll be talking about is taking Géant and speeding it up with GANs and flows and other things. Okay, but you might imagine trying to do this like with a n-body simulation or a hydro simulation. I thought about that, but it's hard to imagine how that would work because, as you'll see for the Géant example, we need like 100,000 showers to get it to fit. I don't think they have 100,000 simulated universes. They maybe have like 10. So yeah.
So the name of the game here is to take in some data and then be able to create a new data set that is like the old data set?
Exactly, in a statistical sense. So drawn from the same distribution.
Okay,
yeah. Okay, so there's other applications, which in the next lecture I'll be talking about anomaly detection. And yeah, and often it's just useful to learn the phase space density. So that's another application which I've worked on. So learn the phase space density of tracer stars. And you could try to get the solve the Boltzmann equation and try to get the mass density of the galaxy out of that. So there's lots of applications. It's a very powerful set of methods. Okay, so there's three main, I would say there's three main paradigms for generative modeling. Of course, people are constantly inventing new things. So this is just, I guess, the current state of the art. So there's three main frameworks which you might want to know about. And, well, they go by the, again, alphabet soup. Okay, so there's three sort of neural network architectures, machine learning architectures that people have come up with to do generative modeling. The first, which I will spend no time on, is something called a variational autoencoder. Okay? And the idea of the variational autoencoder is you basically train the data, or you train a neural network to compress the data, to map the data to a smaller latent space, and then map it back to itself. And the idea is that if it can map the data back to itself through a smaller bottleneck latent space, then it's learned some internal representation of the data that's useful. Okay, and then you can try to sample from this latent space to generate examples. That's sort of how the VAE works. Okay. In my experience, and I think from the literature, this is not so state-of-the-art anymore. I think this preceded these other two. So it's kind of fallen, it's not going to give you the best result. So not so state-of-the-art. So I'm not going to talk any more about that. Okay, so these other two, though, are still pretty state-of-the-art. And so I'm going to talk a little bit about GANs. So GAN here stands for Generative Adversarial Network. And it originated in 2014 in a by now classic paper. Yeah, okay. So good. And then flows is something I'll be spending the most time talking about because it gives you, you'll see, it's more powerful. Okay. Good. So you may have encountered GANs before because they generate fake faces and images. They can do a lot of things with real-world images. Yeah, and the adversarial part of GAN is the key thing. Okay, so it's a pretty neat idea. And the idea is as follows. Okay, so we want to generate. So what does it mean to generate? What does it mean to generate samples? It means we want to map. What does a generative process really mean? We want to map from random noise. Okay, so maybe Z follows the Gaussian distribution, or maybe Z is uniform, but it follows some simple distribution that we specify in advance. Okay, and we want to take that random variable, okay, and we want to map it to the data space. Okay, so we essentially want to generate samples. So we want to generate, there's a function here, G, that maps random noise to things that look like data. Okay, that's the generative process. And the idea of the GAN was, well, if we just write down any old function G, like how do we optimize for good samples, right? So the idea of the GAN, in a nutshell, is, so let's say these are generated samples, and we also have true samples. So these are generated, and these are true, like real images. So they're the training data, yeah? So the idea of the GAN was to introduce another component to the story, the discriminator. So for every time I generate an image, I want to feed it to a discriminator that can tell me, is this image real or fake? So these are real, and these are fake. And so we want the discriminator to be able to tell us, is this image real or fake? And if it can tell the difference between real or fake, go hit the generator on the head, right? The generator must be better, okay? So that's why it's adversarial. These two are opposed to each other. The generator wants to defeat the discriminator, and the discriminator wants to defeat the generator. Good. So the discriminator tries to classify real versus fake, and the generator tries to fool the discriminator. Okay, that's what the GAN is doing in words. Okay, what they realized is that you can accomplish this all with a very nice loss function, which is basically just the binary cross entropy. Again. So it's just the binary cross entropy. But now, so when we train the discriminator, it is just binary classification. But when we train the generator, it only enters in through this term. And what they realize is that at a saddle point extremum, actually makes, if you could achieve a saddle point extremum by training the discriminator and the generator jointly, so at a saddle point, the saddle point looks like this. You want to maximize this with respect to the generator, meaning you're fooling the discriminator as much as possible, and you want to minimize this with respect to the discriminator, meaning you have the best possible binary classifier. So in fact, that's what was so novel about this, is that I can't really draw a saddle in. Okay, so it's achieving a saddle point where you're at the maximum of one of these things and at the minimum of something else. And they showed, there was some math involved. They showed that if you could achieve the saddle point, so at the saddle point, P generated is equal to P data. Yes?
So is this an iterative process, like you go through over and over?
That's right. As with all these things, we train this in epochs, et cetera, and the additional complication is we have to alternate training of the discriminator and the generator. We can't train one all the way and then the other all the way. So we have to train one a little bit and the other a little bit. Otherwise, you would fall off this saddle point. Yeah. Mm-hmm.
How does the discriminator initially know what new things should look like?
It doesn't. It's just random at first. At first, this thing is random and this thing is random. But what they showed is gradually, by sort of fine-tuning these things against each other, you could make this idea work. Yeah. Yeah.
I know one of the difficulties with scans is that they're very hard to train because you're trying to play these off against each other.
Exactly.
Have there been a lot of improvements recently to make it easier to train them, or is it still really challenging?
I think it's still really challenging. Yeah, at least if I read the papers that are proposing alternatives to GANs, yeah, I think it's still very challenging. Yeah, this is an inherent problem with adversarial training in general that I don't think you can get around. Good. Okay, so another thing to point out is that GANs never give you access to this. That is, if I give you a data point, the GAN doesn't tell me what P gen of X is. Okay, it can only sample from it. So I can generate samples using the generator, but there's no function here that magically tells me what P of X is. So that's a sense in which a GAN can learn the probability density implicitly. So this is learned implicitly. Okay. So yeah, it's been what, like 8 years after this paper came out. There have literally been 10,000 papers on GANs. And so I think what people see now is that they are very good at generating realistic images, I guess, because the discriminator can be fooled. But GANs are very unstable to train. They don't have like a very good way of selecting the best model because the loss ends up not being very meaningful because it's not a minimum of anything. And they're actually not very good at learning distributions. So GANs have a famous problem where it's called mode collapse. So if I have like a bimodal distribution that the GAN is trying to learn, oftentimes the GAN will just collapse to one of these modes. And then it'll generate lots of realistic images or examples from this side. And then it takes the discriminator a little time to figure that out. And when the discriminator figures it out, the GAN switches to this mode. And it just keeps, so it gets into like a cycle, yeah? So it cheats, So yeah, so GANs are not great at learning distributions. I think that's an empirical observation. Yeah?
Very quickly, is there a way to throw noise in there?
Throw noise into where?
To make it switch on purpose?
The approach that people have taken to solve this problem is to do other things, but maybe there's something. Yeah, there's literally 10,000 papers on GANs. So no. So I mean, there's other popular approaches that I definitely don't have time to explain that do improve on the mode collapse problem, but they still don't really learn the distribution that well. Yeah.
Are GANs only used for image data?
I wouldn't say, I'm not an expert on all the applications of GANs, so I don't think so. I think probably they use GANs for generating other things too. Like, I'm pretty sure I've seen GANs generate music. So you can use it for audio, for text. Yeah, I think, yeah. Okay, yeah, I think there's nothing special about images here, yeah. As phrased here, there's nothing particularly special about images. Maybe there's something special about natural images, but I'm not sure. Okay, so I really don't have time, but the next thing I want to tell you about are normalizing flows. Okay, I have 2 minutes. Well, I can start. Okay, so the third framework for generative modeling and also density estimation is something called the normalizing flow. And here the idea is, again, we want to, let me draw it this way. Again, we want to map noise to data, okay? In the GAN case, because we're not learning the density explicitly, typically the noise space is smaller than the data space, okay? So the data space might be, I don't know, 1,000 dimensional, and I might use a space that's 100 dimensional or 10 dimensional. The idea of the normalizing flow is more ambitious. The idea is that we want to learn an invertible bijective map between data and a latent space which is of the same size, yeah, so that it's invertible. Okay, so we want an invertible bijective between x and z. So we want a function f which can take us from noise to data, and we also have its inverse being tractable, which can take us from data to noise. That's it. That's the idea of a normalizing flow. Yeah, so right, and the noise maybe is, again, drawn from some Gaussian distribution or from, uniform distribution, some simple distribution. And so basically we want to take the data and morph it through this flow into just a Gaussian or just uniform. It seems like science fiction that this is possible, but it is. And yeah, so basically we want to learn the relation between these probability densities. Right, so through a transformation, right, the probability density is conserved like this. Right, and so all the information, this is some simple distribution, like uniform, and then so all the information is in the Jacobian that maps you from x to z. Okay, so I think I better stop, and we'll pick up from here next time. Yeah.